The golden ratio is a fascinating number that comes from the Fibonacci series. So, as you may have already probably seen, Fibonacci numbers can create these lovely, pleasing spirals called Fibonacci spirals. And it turns out that lots of artists have used these spirals and these proportions over centuries in order to create really pleasing artwork. Painters like Johannes Vermeer painting The Girl with the Pearl Earring, of course Leonardo da Vinci's Mona Lisa, The Man, and The Annunciation all have elements of Fibonacci spirals and the golden ratio in their work. But modern day artists use this pleasing golden ratio Fibonacci spiral in their artwork as well. The Twitter logo, the Apple logo, the Pepsi logo, the National Geographic logos are all using Fibonacci spirals and the golden ratio. And of course, as you've probably studied, the golden ratio and Fibonacci numbers appear in nature over and over and over again. So let's look at where the golden ratio comes from, given the Fibonacci numbers. Let's see how our string of Fibonacci numbers gives us the golden ratio. So here I have listed the string of Fibonacci numbers starting at 1 and going up to 144. Where we get the golden ratio is by dividing two consecutive Fibonacci numbers, the bigger one divided by the smaller one. Since 1 divided by 1 is a little bit straightforward, let's start with 2 divided by 1, which is 2. Okay, and then let's go to the next set. So 3 divided by 2 is 1.5. And then the next set, 5 divided by 3 is 1.67 repeating, 1.66666. Let's skip ahead just a little bit. Let's do these two. Let's do 55 divided by 34. When we do that, we get 1.61764. Kind of close to 1.67 that we had back here. Well, let's do another one. Let's do these two. Let's do 89 divided by 55. When we do that, we get 1.618181818. Man, that's really close to 1.617. And the only other one I can fit on here, 144 divided by 89. And we're going to get 1.617. Whoops. 17977, rounding a little bit. And what I want you to notice is these numbers, the further we get in our Fibonacci sequence, strangely, this ratio is converging to a constant number that's actually rather small, 1.618 about. The golden ratio is a number that's really close to 1.618. In the next set, I'll show you exactly where that number comes from. Great. Here is our Fibonacci spiral created with rectangles and squares from Fibonacci numbers in our sequence. And we're going to get to do a little bit of algebra here. So I'm going to call the width of the large square here A. This is the one. It happens to be 34 by 34. And this next smallest one, 21. So remember, if we did, let's do 34 divided by 21. That's not very far along in our sequence. We're going to get 1.619, which is really close to our golden ratio number. So let's generalize this. Let's say we wanted to do the bigger side, which would be A plus B, divided by the smaller side, which would be A, for a generic case, not necessarily 21 and 34. So A plus B divided by A. To get our golden ratio, this should be equal to the previous ratio, let's see, of this side here, where A is the longer side and B is the shorter side in that smaller rectangle. So let's see, A is the longer side divided by B. Now it takes some algebra to solve this proportion, so let's clean this up a little bit and let's make our numbers a little bit easier to deal with. Better. Okay, so to make these numbers a little bit easier to deal with, let's have ABX and let's have B just be the number 1, simply because it's easy. Remember, to solve a proportion like this, we're going to clear our fractions. So we're going to multiply both sides by our denominator x, so that x cancels with the previous denominator. That gives us x plus 1 equals x squared. Okay, so it might have been a minute since we've done some algebra here. So I'm going to get 0 on one side. This is quadratic, so x squared minus x minus 1 by subtracting the x and subtracting 1 from both sides. And then I'm going to use the quadratic formula. Remember, that's the one that goes negative b plus or minus the square root of b squared minus 4ac divided by 2a. And plugging in, let's see, it looks like a lot of 1s and negative 1s. A is 1, the middle coefficient's negative 1, and c is negative 1. We get 1 plus or minus the square root of negative 1 squared, so 1 minus 4 times 1 times negative 1, all over 2 times 1. Okay, this is actually great. This is negative 4 times of negative 1, so that'll be a positive 4. So we have 1 plus or minus the square root of 1 plus 4 will be 5, all over 2. Cool. That, ladies and gentlemen, is the golden ratio. Plug that into your calculators and you should get a number that's really close to 1.618. Cool. So this is our phi. One thing it might be nice to do is to be able to tell if a rectangle that you're looking at is, in fact, a golden rectangle or not. Now, certainly, if the sides of the rectangle are Fibonacci numbers, consecutive Fibonacci numbers, say 144 centimeters and 89 centimeters, that would certainly be a golden rectangle. But what if the numbers aren't Fibonacci numbers? What if, let's see, let's erase this. What if instead, what if we had the numbers 84.1 centimeters and 52 centimeters? Is this rectangle a golden rectangle? So here's how we tell. We're going to take the larger side, 84.1, and just like we did in the previous problems, divide it by the smaller side, 52. And see if we get something that is close, approximately close, to phi. Plugging that into my calculator, I get 1.6173. That is pretty close to phi, so I think we can safely say, yes, this is at least approximately golden. Let's try one more example. Okay, we'll put our golden rectangle over here in the corner, and let's look at this new rectangle. Again, 14 feet by 6 feet. They're not consecutive Fibonacci numbers, but neither was the previous one, so maybe this will be golden. I'm going to take the larger number, 14, divide by the smaller number, 6, and see if I get something close to 1.618. That's my goal. But when I plug that into my calculator, now I get 2.33 repeating, which would be not a golden rectangle.